All right, it's time for discussion 2-1, classifying matter. All right, so let's first look at states of matter. There's 3 states: solid, liquid, and gas. What I want you to be able to do is describe the shape, volume, and energy of the particles. So, for gas, the shape is indefinite. What that means is the shape can change. Think about a balloon. If you have a gas in a balloon, you can squish the balloon with your hands and change the shape of the gas. So we would say that gases have an indefinite shape, or a shape that can change or conform to the shape of a container that we put it in. When we think of the volume of a gas, we know that if you heat a balloon, that balloon will grow. That's kind of how a hot air balloon works. A hot air balloon just has air in it, and there's a flame underneath that heats the air. As the air is heated, it spreads out to a larger volume, making the air in the balloon less dense than the air outside the balloon, which is why the balloon floats. So we would say that gases also have an indefinite volume because we can change the volume of a gas. Now, in terms of energy of the particles, we're talking about how fast they're moving around. And you can see here from this diagram that in a gas, the molecules or particles are more spread out, and they're kind of zipping around like crazy, moving very, very quickly. Now, let's look at a liquid. Now, we know that if I had a glass of water and I poured that glass of water into let's say a glass that's shaped like an elephant, the water would take the shape of the elephant or whatever container you put it in. So since the shape of a liquid can change, we would also say that it is indefinite. Now with volume, we have to think about the proximity of different particles in the sample. For example, in the gas, they're all spread out. In the liquid, they're much closer together. Because they're already very close together, it means they don't have a lot of room to move. Think about being in my classroom with only 2 other kids, you would have a lot more space to move around. But if the kids were all shoulder to shoulder filling the room, there wouldn't be as much place for you to move. So the volume of a liquid, will always be definite. The volume will not change. Now, in terms of movement, gases are crazy moving. Solids, you can probably imagine, don't move that much at all. So for liquids, we would say that they have medium energy. We're just really concerned with the energy compared to the other phases. And then for solids, well, if I take my cell phone and set it down here on the desk, its shape is going to stay the same. So I would say that all solids have a definite shape. The phone also will not shrink or grow, so I would say that solids have definite volume. And in terms of the energy of their particles, the particles do vibrate in place, but they don't move in relation to one another. So we would say that they have the lowest energy of the 3 phases. All right, so we can actually predict the phase that a particular substance will be in using a plot called a phase diagram. We can see the phase diagram is a plot of pressure on the y-axis and temperature on the x-axis. So there's a couple different things we need to know about this. First of all, if we were given a pressure and a temperature, if we wanted to find out what phase the substance was in, we would just have to plot the point. We can see that the graph is separated into 3 distinct areas: solid, liquid, and gas. If the point falls in the liquid region, we would say that it's a liquid. If it falls in the solid region, we would say that it's solid. Now, there's a special point on every phase diagram called the triple point, and that is the point where all 3 of the curves in the graph intersect. And at the triple point, all 3 phases of matter, solid, liquid, and gas, all exist at the same time. Very cool. So we can also consider what occurs as we change pressure and temperature. So we know if you take a solid and heat it, eventually it will melt. If you continue to heat it, eventually it will evaporate or boil. So whenever we're looking at this curve, we have to consider what the change would be when we cross a particular boundary. Well, if I had a point in the solid region and I kept the pressure constant but increased the temperature, then the point would slide from solid to liquid. So we know that if we cross this line, our substance would be melting. Now we also have to consider what happens if we're going in the opposite direction. So if we go from liquid to solid, we call that freezing. So if we had a point cross that line, we would say that our substance froze. We can also do the thing at the border between liquid and gas. We know if we go from a liquid to gas, we call that evaporating. And a gas going back into a liquid is called condensing, That's why when you have a cold glass of water on a hot day, the water that forms on the outside of the glass is called condensation. Now there's another phase change that you need to know about, and that's the phase change that would occur if we have a point crossing this line here. So this is a transition directly from solid to gas without going through the liquid phase in between. We call that subliming. The reverse process of that is called deposition, but you only need to know about subliming. All right, so practice. Pause the video and see if you can work out both of these problems. All right, so the first one gives us a temperature and a pressure, and it says, what will the state of matter be? So it says 200 Kelvin. So here we are, 200 Kelvin is probably right around here, in between 197 and 216, and 5.2 atmospheres. Boop. When we plot our point, it ends up right here. So we would say our matter is in the solid phase. And then it says, what phase change is occurring along line C? Well, here is line C right here. And we can see that line C is the border between liquid and gas. So of course we know going from liquid to gas is evaporating or condensing, depending on which way you're going. If you're going from liquid to gas, it's evaporating. If you're going from gas to liquid, it's condensing. All right, now let's look at a heating curve. A heating curve is a plot that shows us what happens to the temperature of a sample of matter as heat is added to it. So here we have time on the x-axis. We could also say that on the x-axis here, we're talking about heat. So as we add heat, we're increasing in the x direction. We can see in the y direction, we have temperature. So as we add heat, the temperature will go up. So what you need to be able to do with the heating curve is label each region of the graph. We can see we have region AB, BC, CD, and so forth. So between points A and B, we're at the lowest possible temperature. So think about water. When water is at the lowest possible temperature, it's ice, solid. Now, as heat is added to the solid, it will begin to melt. So the first thing that happens after segment AB is BC, which is our substance melting. Once the substance has completed melting, it's now going to be a liquid. So region C to D is liquid. If we add enough heat to a liquid, it will eventually begin to evaporate. And once it is fully evaporated, it turns into a gas. So the diagonal portions here represent the phases of matter. Pretty easy to remember because there's 3 phases of matter and there's 3 diagonal portions in the curve. The flat sections are where the phase changes are occurring. And of course, if going from point D to point E is evaporation, then going backwards from point E to point D is condensation. Same thing with B and C. If going from B to C is melting, then going from C to B is called freezing. So again, you just need to be able to analyze or label these curves. Now, I know that boiling or evaporating happens at point D, between points D and E. So if I wanted to know what the boiling point of this substance would be, I would just have to find what temperature that lies along the y-axis. The same thing with freezing. All right, so matter. Matter can be first of all, is anything that has mass and takes up volume. So all the things that we're used to in our daily experience counts as matter. Matter can be broken up into 2 main categories: pure substances and mixtures. Pure substances we already looked at back in Unit 1, but a pure substance can either be an element or a compound. When we say pure substance, what we mean is something that's made up of only one type of particle. So if you have a chunk of copper, we know that that's an element. Every single atom in that structure is copper. There's nothing else mixed in. The other thing that matter can be is a mixture. And there are 2 types of mixtures: a heterogeneous mixture and a homogeneous mixture. And we'll talk about each one of those. So this slide should look pretty familiar to you. We actually covered this in Unit 1. I'm going to review it now because elements and compounds are our two types of pure substances. So of course, elements are made up of atoms. Atoms are the simplest form of matter, which means they cannot be broken down into simpler substances. We can find all the elements on the periodic table of the elements. And the symbols for elements will be made up of only one capital letter. So examples, O2. Remember, some of our elements exist as what are known as diatomic molecules. You can tell that oxygen is an element, though, because in the formula for oxygen, there's only one capital letter. Na is sodium, S is sulfur, and H2, another one of our diatomics, is hydrogen. Now for compounds, compounds are made up of molecules. Well, what is a molecule? Molecules are atoms of different elements chemically bonded together. So here we have this yellow element and this orange element. There's a chemical bond in between those two atoms holding them together. Now we can break a molecule down into simpler substances because we can break the molecules down into the atoms that make them up. And the symbols, since they contain more than one capital or more than one element, will contain more than one capital letter. So examples of compounds: water, carbon dioxide, glucose, or sulfur dioxide. All right, now let's talk about mixtures. Well, what is a mixture? A mixture is a substance that is made up of more than one type of particle physically mixed. So if we can look at our diagrams here, I have pink-blue molecules, I have white atoms, and black atoms. They're all mixed together, so we say that it's a mixture. Now, if your mixture is heterogeneous, what that means is that you have a non-uniform particle distribution. The prefix hetero means different. So if I look at the heterogeneous mixture here, there's no pattern I can see among these particles. They're randomly distributed, so I would say that this mixture is heterogeneous. Now, in a heterogeneous mixture, you will have large particle size. In other words, the particles that make up the mixture are large comparatively, and you can separate them out with a filter. So think things like Raisin Bran, right? Raisin Bran is a mixture of flakes, raisins, and milk. We could separate the raisins and the flakes from the milk by passing them through a filter. The milk will pass through the filter, which will leave behind the flakes and the raisins. If you want to separate the raisins from the flakes, you just have to pick them out with your hands. So the one thing about a heterogeneous mixture is it will always settle out over time because of gravity. The heavier particles will settle on the bottom. So try that with your bowl of cereal. Pour half a bowl of cereal in a glass. At first, the cereal will float, but once it becomes waterlogged, eventually it will separate. So what you're going to see in a heterogeneous mixture over time is two distinct layers. Think oil and vinegar. So examples, Raisin Bran, like I mentioned, human beings, we are heterogeneous mixtures, and soil. So soil will have dirt, roots, pieces of wood, animal bones, all this other stuff mixed in randomly, so we would say that it's heterogeneous. A homogeneous mixture is the opposite. It has a uniformed or patterned particle distribution. So here's an image of a homogeneous mixture. We can see it's made up of white and blue atoms, where each white atom is surrounded by exactly 4 blue atoms in exactly the same way. There's a discernible pattern here. It looks the same throughout, which is why we say that it is homogeneous. So one thing that makes a homogeneous mixture is the fact that it has very, very small particles. That means a homogeneous mixture cannot be separated with a filter. Milk is an example of a homogeneous mixture. When you poured your Raisin Bran through the filter, the milk passed right through intact. You could drink it. It's still milk. But the bigger particles were caught in the filter. A homogeneous mixture will not settle out over time. And a homogeneous mixture has a special name called a solution. So different types of homogeneous mixtures, salty water. Again, if you put salt in water and stir it and look at it, it looks the same everywhere. Salt will not settle on the bottom of the container. It dissolves and stays dissolved. Air is a mixture of different gases. Air to me looks the same everywhere. And steel. Steel is an interesting example. Steel is actually a mixture of iron and carbon. All right. So there's actually two types of heterogeneous mixtures as well. If you're a heterogeneous mixture, you could either be a suspension or a colloid. The thing that depends on whether you're a suspension or a colloid is the particle size. So if the particles are their largest possible size, you'll have a suspension, and the particles will quickly settle to the bottom. Think things like vegetable soup or Italian dressing or muddy water. If you have a colloid, colloids have medium-sized particles, so they're almost kind of in between a homogeneous solution or a suspension. So in a colloid, you're going to get some settling over time, but you won't get complete settling. So think of things like milk or fog, orange juice with pulp in it, blood, and so forth. All right, so let's take a minute and pause. I have 4 or 5 items here: vegetable soup, muddy water, fog, Kool-Aid, and Coca-Cola. I want you to determine whether or not those are heterogeneous or homogeneous mixtures. Now remember, a heterogeneous mixture will settle over time. A heterogeneous mixture can be separated with a filter. A homogeneous mixture will not settle over time. A homogeneous mixture cannot be separated by a filter. So when you're doing this, think, will it settle over time? Will it separate into 2 distinct layers? Or could I separate it with a filter? So pause the video and see if you can work that out. All right, so vegetable soup, we can filter vegetable soup, so I know that that is heterogeneous. Coca-Cola is homogeneous. Think about it. If you pour Coke through a filter, if you try to drink it on the other side, it's still Coca-Cola. Muddy water is an example of a heterogeneous mixture. If we take water and pour a bunch of dirt in it to make muddy water, eventually the mud will settle on the bottom. Kool-Aid is also a homogeneous mixture. Now, when I say it'll settle into 2 distinct layers, think of this. You put Kool-Aid into the fridge, and it stays there for a few days. If it sits there for a few days, does it get to the point where you have really nice red Kool-Aid on the bottom and a layer of clear water on top? I know I never see that, which tells me that Kool-Aid is homogeneous. And down here we have our example of fog. This is a heterogeneous mixture. You can tell that because fog is literally moisture from the air, clouds essentially settling on the bottom, on the surface of the earth. All right, so let's talk about how we separate mixtures. So first of all, when we're separating a mixture, we have to consider whether it's going to be, we need to, a physical change or a chemical change to separate that mixture. So let's think of my favorite mixture, Raisin Bran. If I want to separate the flakes from the raisins, I can just pick the raisins out with my fingers. That is a physical change. The reason we can separate a mixture with a physical change is because the particles in the mixture are physically combined. They're not bonded together. So when we're separating a compound, we actually need something called a chemical change because the elements in the compound are chemically combined together. And we'll talk a little bit about physical and chemical changes in topic 2 of this unit. All right, so now let's talk about different ways to separate a mixture. The first is called filtering. We're all pretty well familiar with filtering, I assume. We use filtering to separate a heterogeneous mixture, usually one of a solid and a liquid. So because the particles in a heterogeneous mixture are so big, they will not fit through the pores in the filter paper. Very much like a COVID virus is too big to fit through the pores in the mask, which is why we always wear our masks in the proper way. All right, so you can't separate a homogeneous mixture with a filter because in a homogeneous mixture, the particles are just too small. They are small enough to pass through the pores in the filter. Now, chromatography is separation based on the movement of different particles over a medium, usually paper or wool. So think of this kind of like a race. Because of a bunch of different properties of different compounds, different masses, different densities, etc., some will move along a medium faster than others. So if you let your substance run over a medium for a certain amount of time, you're going to get separation based on how fast they move. So black ink and a marker is actually a mixture of all different colors of ink. So if you do chromatography with black ink, what you would see is a nice rainbow as all the colors separated from each other. So it's used for separating the colors that make up ink a lot of times. In chemistry, it's really used for more advanced things, but for all intents and purposes for this class, you can just think of it like separating colors. All right, finally, distillation is separation based on different boiling points. So let's say I have a homogeneous mixture of two or more liquids. I have to assume that the two liquids have different boiling points. So to distill, we put our mixture of two liquids into a flask and heat it. Whichever liquid has a lower boiling point will begin to boil first. The fumes will travel up the flask and reach this diagonal tube here called a condenser. Now this condenser has water flowing in and around the tube, so it's a cold environment in there. So when the gases come up, they cool and condense in the condenser, and they get a little gravity assist to be separated into this flask. So think of making alcohol, for instance. We use distilling to do that because the alcohol will boil at a lower temperature than the water, so we can separate a mixture of water and ethanol doing that. And that is it for discussion 2.1. Thank you so much, as always, for watching. If anybody has any questions, please bring them to class.